Howdy. This video is on nuclear reactions. Nuclear reactions describe important processes that occur in stars, bombs, nuclear power plants, nuclear medicine, etc. After the Big Bang, there was just hydrogen and helium. All the other elements were products of nuclear reactions that occur in stars. After watching this video, you should be able to balance nuclear reactions. We'll see the key to balancing a nuclear reaction is making sure that the mass number sum products reactants is the same, and the charge for the products reactants are the same. You should be able to determine if an isotope is stable or unstable based on its number of protons and neutrons. And also based on the number of protons and neutrons, you should be able to predict the type of decay a radioisotope will undergo. So for chemical reactions, it's all about breaking and forming chemical bonds. Only electrons are involved in the forming and breaking of chemical bonds. It's all about the electrostatic interaction. Remember, for electrostatic interaction, like charged particles repel, opposite charged particles attract. For nuclear reactions, elements can be converted from one to another. Protons, neutrons, and other fundamental particles may be involved. Quarks are kept together by the strong force. Nucleons are kept together in a nucleus by the strong force. Remember, a nucleus contains protons and neutrons. Protons are positively charged, neutrons are neutral. And so protons repel each other based on electrostatic interaction, but attract each other based on the strong force. So the strong force is stronger than electrostatic interaction, and that's why nucleus stays intact. But in nuclear reactions, you have the strong force, which is much stronger electrostatic interaction, and that's why you can have much higher energies. And so in chemical reactions, it's electrostatic interaction, and so the amount of energy is relatively small, and rates of reactions are normally affected by temperature, pressure, and the presence of a catalyst. For nuclear reactions, it's about the strong force, and so the amount of energy can be really, really large, either expelled or absorbed. And reactions are not normally affected by temperature, pressure, or presence of a catalyst. Now, some nuclear reactions that we'll talk about are alpha emission, beta emission, positron emission, electron capture, induced nuclear fission, and nuclear fusion. Now, the top four ones are radioactive decays, and all radioactive decays are first-order process, so they follow first-order kinetics. Now, when you see the term emission, sometimes I'll use emission or decay. I'll use those interchangeably. So you could be talking about alpha emission or alpha decay. If you see emission or decay, it just means that the radiation is a product. So alpha emission means the alpha particle is in the products. And again, emission and decay I'll use interchangeably. Capture means the electron is a reactant. And so for this type of radioactive decay, what's happening is that electron is actually captured by the nucleus, and you have an isotope going from one isotope to another isotope. But for all nuclear reactions, even the fission and fusion, the sums of the mass numbers have to be the same products reactants, and the sum of the charges have to be the same for the products and the reactants. And so we can look at an example of a nuclear reaction. This is a balanced nuclear reaction. And so the charge, that bottom number, is the same products reactants, right? In the reactants, we have a 5, and in the products, 6 minus 1 gives us 5. And so remember, a beta particle's electron has a -1 charge. The 6 is the number of protons in the nucleus, which is the charged nucleus. This 5 means that the boron has 5 protons in the nucleus, atomic number 5. And so a balanced nuclear reaction, the sum of the charges of product reactants have to be the same. And so we have 5 and we have 5. And the other thing for a balanced nuclear reaction is that the sum of the mass numbers have to be the same. So remember, the mass number is the number of protons plus neutrons. And so boron 12 has 5 protons. All boron atoms have 5 protons. And boron 12 has 7 neutrons. Carbon 12, you have 6 protons. 12 minus 6 means you have 6 neutrons. And so for the reactants, we have a sum of mass number of 12. For the products, we have 12. And so that tells us this is a balanced nuclear reaction. the sum of the charges are the same products reactants, and the sum of the mass numbers are the same for the products and the reactants. And so all borons have 5 protons. 12 minus 5 gives 7 neutrons. And so during this reaction, we're having a boron change into a carbon. We're also having a neutron changing into a proton. Now, if you remember, a proton is composed of 2 up quarks, 1 down quark. A neutron is composed of 2 down quarks and 1 up quark. And so if a down quark from a neutron changes into an up quark, that neutron is changing into a proton. And so it's kind of cool. We can think about this reaction on 3 different levels. We can think about in terms of boron changing the carbon. We can think about it as a neutron changing into a proton. Or we can think about as a down quark changing into an up quark. Now this is a beta decay. You have a beta particle as a product. And the beta decay was not created, or it was created when the down quark changed into an up quark. It did not exist before this nuclear reaction happened. But please remember, for a balanced nuclear reaction, the sum of the mass numbers have to be same products reactants, and the sum of the charges have to be the same products reactants. And so when you're asked what kind of decay process, all you have to do is balance the nuclear reaction. And so looking at this one, we have cobalt 60 going to nickel 60. And so that tells us that the mass number has to be 0 of what's being formed. Now, cobalt has atomic number 27, positive 27 charge of nucleus. Nickel, 28 protons, positive 28 charge of nucleus. And to make the charges the same products reactants, we must be forming a particle with a -1. And so that tells us this must be beta decay. And so making sure that some of the product of the mass numbers of the same products reactants, some of the charges, same products reactants, actually just enables us to determine what is formed in a nuclear reaction. Now, if we look at this one, again, all I have to do is balance. And so we have 222 minus 218 means we have 4. 86 minus 84 is 2. And so a mass number of 2, a +2 charge, and that would be an alpha particle. Again, remember that 2 protons, 2 neutrons are extra stable, and so that's what a helium-4 nucleus is composed of, 2 protons plus 2 neutrons. It's also what an alpha particle is composed of. We can look at another example. And so again, we just balance. And we have 246 plus 12 gives us 258. 258 minus 254 gives us 4. And so we must be forming 4 neutrons. 96 plus 6 is 102. And so neutrons have 0 charge. We can go through a slew of these. And again, you can determine these numbers by just making sure that's a balanced nuclear reaction, that you have the same mass number, products, reactants, and you have the same charge, products and reactants. And so a stable isotope is one that does not spontaneously decompose into another isotope, and I'll use isotope and nuclide interchangeably. A radioactive isotope is one that does spontaneously decompose because it is not stable. Now, we can actually use 6 points to describe, or rules of thumb to describe stable isotopes. And so the number of neutrons is equal to or greater than the number of protons, except for hydrogen and helium-3. Up to atomic number 20, the number of protons and neutrons are nearly equal, so it's a 1-to-1 ratio. And as you get to bigger isotopes, we'll see that the ratio of neutrons to protons actually increase. You start needing more neutrons when you have more protons. Rule 3, the zone of stability contains all stable nuclides, but some nuclides in this band are unstable. And so if we look at the zone of stability, so we've plotted number of neutrons versus number of protons. Now the black line shows you the 1-to-1 ratio. As for the first 20, they're close to a 1-to-1 ratio, so you'll need 1 proton to 1 neutron. And then notice that the relative number of neutrons increases to the bigger isotopes you get. And so the band stability contains all stable nuclides, but some in the band are unstable. So if we zoom in on the band, we see that we do have some unstable isotopes. So the band contains all stable isotopes, but some isotopes in the band are unstable. Rule 4, certain numbers of protons and neutrons called magic numbers confer unusual stability. And so if a nuclide had 50 neutrons or 50 protons, it's a little more stable than it would be otherwise. Now, the way of thinking about this one is that the nuclear structure is kind of similar to the structure of an atom, where in atoms you have shells of electrons. You also have shells of electrons in the nucleus. And that's why you have these magic numbers. Technetium and promethium and all elements beyond bismuth have no stable isotopes. Nuclear stability is greater for nuclides containing even numbers of protons, even numbers of neutrons, or both. And so technetium, promethium, plus everything after bismuth is radioactive. There's nothing stable in these red elements. You should also remember everything after uranium. So uranium is element 92, so you go 93 on, and then go up here. Everything in red here is man-made. They're not naturally occurring. And I mentioned that even numbers are more stable, and so the number of stable isotopes with even number of protons, even number of neutrons is 157. With one odd number, one even number is about 103. And with two odd numbers is just 4. And so having even numbers is extra stable. Now we can use these 6 rules to actually predict what type of decay an element will undergo. And so one question you could be asked is, by what process will lithium-9 decay? Now the first thing we have to look at is the number of protons plus neutrons. And so lithium is element number 3. And so that means we have 3 protons. 9 minus 3 gives us 6, so that means we will have 6 neutrons. Now there's 2 ways of doing it once we're here. One way is, okay, let's go to the band of stability and see where we're at relative to it. And so 3 protons, 6 neutrons, that would put us up here in the upper left corner. And so it's going to go undergo decay, trying to get closer to the band of stability. And so that means a neutron is going to change into a proton. And so by beta decay, a neutron changes into a proton. Another way of doing it is just by looking at these numbers. Remember, for first 20, it should be 1-to-1. And so we got too many neutrons relative to the protons. And so that would tell us a neutron would change into a proton. And if you wrote down the reaction, you'd see to balance it, you have to have a beta decay. And so you went from having 3 protons to 4. So a neutron changed into a proton. That's why the mass number didn't change. If a neutron changes into a proton, it means a down quark is changing into an up quark. Now, to balance everything, it has to emit a beta particle. We can ask the same question about oxygen 14. And again, the first step is number of protons plus neutrons. And so oxygen is element number 8. We have 8 protons in the nucleus. And so 14 minus 8 gives us 6. And so again, easy to remember, for first 20, it should be 1-to-1 ratio. And so what this tells us is that we have too many protons relative to neutrons. And so a proton will change into a neutron, meaning up quark changes into down quark. Now there's 2 ways you can actually do that. You can either do electron capture or positron emission. Now another way of solving it is, okay, 8 protons, 6 neutrons puts us down here in the lower right. And so if you're down here in lower right, you want to go up and to the left. And so that means you're going to go electron capture or positron emission. Now, if we balance it, so electron capture, mass number is same, so that gives you nitrogen 14. Positron emission, and so we balance that. We also get nitrogen 14. And so in this class, we can't really distinguish between electron capture or positron emission. But again, another way of doing this problem is by going, okay, a proton has to change into a neutron. And so that means you're going from 8 to 7. You balance it, and then that would mean this has to be a positron. And during both processes, a proton changes into a neutron. So again, an up quark changes into a down quark. You can also be asked about, okay, by what process will curium-247 decay? Now we'll assume if it's this big, it's just going to want to lose weight as fast as possible. So we'd assume an alpha decay. And so if you remember, if you're down here, positron emission, electron capture. If you're over here, it's beta emission. If you're up here, then it's going to be alpha decay. And so we can balance the reaction now. 247 minus 4, that gives us 243. 96 minus 2 gives us 94. Element 94 is plutonium. And so for nuclear reactions, you always make sure that the mass numbers are the same products reactants and the charges are the same products reactants. And again, to determine or predict the type of decay, you just look at the number of protons and neutrons and try to figure out, do you want a proton changed into a neutron, or a neutron changing in a proton, or if your atomic number is bigger than 83, we'll assume that an alpha particle is being emitted. And so you can look at number of protons, neutrons, try to figure out where you're on the band of stability, and then use those rules to predict the type of decay. Now this is a bit of a simplification. You can often have more than one type of decay, but this is what we'll use. And so after the Big Bang, there was just hydrogen and helium. All other elements were products of nuclear reactions. For nuclear reactions, the sum of the mass numbers and the charges have to be the same for the products reactants. And so you can predict the type of decay based on the 6 rules that we went through. I hope that was helpful.